Today I will be discussing Lab 4 Oscillations. I will begin by introducing the table of contents. I will start with an introduction, then move on to the physics principles of this lab, then talk about a brief overview of the experiment, then move on to the computational code, then compare the two models, the computation and experimental models, talk about sources of errors, and then finish off with the questions. So, the introduction. The purpose of this lab was to observe and analyze the motions of a system containing a mass and a spring, with the mass oscillating in an arc. Then compare the experimental results to a computational model to determine if the energy principle is satisfied. And then some physics principles in this lab were Newton's second law and the energy principle. So for the physics principles, Newton's second law is a force is equal to its change in momentum over change in time. And then the energy principle states that energy cannot be created or destroyed, but it may be transformed into other types of energy. For a brief overview of the experiment, the system in this case was identified to be the mass, the spring, and Earth. The surroundings were nothing. And then the initial conditions for G, the spring constant, the relaxed length, and then M were all given. And then the initial position was found to be negative 0.164 meters in the x direction, and then negative 0.616 meters in the y direction. And then this was found using the tracker. And then the initial velocity was 0 meters per second because the system started at rest. The result of the experiment was that energy remains constant at zero, meaning the experiment does not violate the energy principle, and this is because energy was not created or destroyed in this experiment. And then this is the experimental model using the tracker app. And then here you can see the graphs that I got, and then you can also see the initial conditions I got. And now for the computational model, I started off with using the kinetic energy formula, then the gravitational potential energy formula, um, and then I used the spring potential energy formula and added all of those up to get the total energy. And then here, this is the F spring formula. This is F gravity, and then you add those two to get the net force. And then here is the velocity update formula, and then this is the velocity of or the position update formula. And then here's the other part of the computational code. And then for a comparison of the two models, in the first graph, you can see that the X position of the experiment is below the one of the model. And an error of this is the system is not closed or isolated from its surroundings, so other forces can be acting on the system. And then for the Y position does seem to be a bit lower than or the Y position for the experiment does seem to be a bit lower than the model, and this could be because of inaccurate center of masses from the tracker. And then the question, is the energy principle satisfied? In this case, yes, the energy principle is satisfied. And then here, the orange line, which represents the change in energy, is constant at zero. And then there's no external forces acting on the system, so the change in energy must be equal to zero, which means that energy was not created or destroyed in this experiment. So yes, the energy principle is satisfied. So for a comparison of the oscillation periods, so for an oscillation is a period which goes from the lowest point to the next lowest point to the next lowest point to the next lowest point. So in this case, there would be three oscillations. So 3t would equal to 4.843 seconds, and then t would equal 1.614 seconds. And then you would use the K formula, and once you plug in everything, you would get 6.092 newtons per meter. And then you do the same thing in the Y direction, and you would get and you would use the K formula and then plug everything in and get 7.16 newtons per meter.